This is lesson 5 in unit 6. We're looking at solving radical equations today. Anytime we have an equation that has a variable in the radicand or has a variable with a rational exponent, we can say this is a radical equation. For example, x cubed plus 1 equals 65 is an example of a radical equation. When you have a radical equation in which the radical has an index of 2, this is known as a square root equation. So the square root of x equals 9 is a square root equation. Our first example is the same thing, but we could also go back and say if we had the cube root of x is 8, that could also be an example of a radical equation. Here you see an organized list of steps for how to solve radical equations. First, we want to isolate the radical to one side of the equation, and then we want to raise the equation on both sides to the power of the index, and then next we would solve for the variable. Whenever you have equations that have a rational exponent, we want to use the reciprocal of that exponent. So if your power is m over n, we want to raise the power to n divided by m, as shown here. So let's jump right into the lesson and first look at solving a square root equation. In example 1, we want to isolate the radical to one side, so we're going to get the 5 to move to the other side by adding 5 to both sides. So radical 4x plus 1 is equal to positive 5. And our index is 2, so we want to square both sides of the equation. So 5 squared will be 25. And the square root of 4x plus 1 quantity squared is going to get 4x plus 1 out from the radical. So the half power and the power 2 undo each other. They're inverse operations. Next, we're going to solve for the variable x. So 4x is 24 when x is 6. And you want to check that in the original equation to make sure that 4 times 6, that's 24 plus 1. So the square root of 25, which is 5, minus 5 is definitely equal to 0, and that does check. You might want to turn off the video and try example 2 on your own. Here we want to subtract 4 from both sides of the equation to isolate the radical. 7 minus 4 is 3. Then we're going to square the square root to get the expression or the argument. 2x minus 5, we want to get that out from under the radical sign by squaring that side. But whatever we do to the left, we have to do to the right. And that gives us 3 squared, which is 9. So adding 5 to both sides, that's 14. And dividing both sides by 2 is 7. And then you want to quickly check that 2 times 7, that's 14. Minus 5, that's 9. So the square root of 9 is 3. And 3 plus 4 is definitely 7. And that does check. In example 3, we want to convert between the two forms. So first, to isolate the radical, we want to divide both sides by 2. So x plus 3 to the 2/3 power is equal to 4. And this is a rational exponent. So to undo the rational exponent of 2/3, we would need to raise the left side to the 3/2 power. But whatever we do to the left, you have to do the same thing to the right. So the 4 needs the 3/2 power as well. So we have x plus 3 to the 6/6 power, that's 1. And that gets our argument out from the radical. And then 4 to the 3/2 power is simply saying the square root of 4 cubed. Well, the square root of 4 is 2, and 2 cubed is 8. So x plus 3 is 8 when x equals 5. And I'll save the checking to you, but that does work out to be true. Here in example B, we have 5 times x plus 1 to the 3/4 power. We're going to move the 1 to the 39, and that gives us 40. Then dividing both sides by 5, we end up with x plus 1 to the 3/4 equals 8. And I want to get rid of the 3/4 power, so we need to use the 4/3 power to eliminate that radical, and also 8 to the 4/3 power on the right. So x plus 1 is equal to 8 to the 4/3 power. So we're looking at the cube root of 8, that's 2, and 2 to the 4th, that's 16. So x plus 1 is 16 when x is 15. And again, I'm going to leave the checking to you so you can verify that this is a true statement. We'll move on to using radical equations next. Here we have a practical application. The size of meteor crater in Arizona can be modeled by this equation where d is the diameter of the rim in meters and the volume is in cubic meters, and we have this formula here we can use. So the crater has a diameter of about 1.2 kilometers. So 1.2 kilometers is the same thing as 1,200 meters, and that's our diameter, and we need to be in meters to use the formula. So we're going to substitute 1,200 for d, and 2 times the cube root of the volume divided by 3/10 under the radical. So dividing both sides by 2, we find 600 is the cube root of v divided by 0.3. So cubing both sides, if we cube the left and cube the right, we're going to end up without a radical. So 600 cubed is 216 million, and that's volume over 3/10. Whoop, can't write here. Let's get that corrected. 0.3. So multiplying both sides by 3/10, the volume is 64,800,000. Whoop. Need 3 more zeros. 800,000 cubic meters. The volume of meteor crater. Maybe we could fill it up with popcorn or something interesting. Suppose the diameter of a similarly shaped crater is 1 kilometer. So that's 1,000 meters. Our volume is, the diameter is 1,000 meters. And our formula is 2 times the cube root of the volume divided by 3/10. So dividing both sides by 2, we have 500 is the cube root of volume divided by 3/10. So we want to cube both sides to eliminate the cube root, and we have 125 million is the volume divided by 3/10. So multiplying both sides by 3/10, the volume is 37,500,000 cubic meters. Like we saw earlier in the unit, we want to be able to check for extraneous solutions. In example 5, we have 2 issues going on. First, we have a radical, and then we've got a 3, which also has to be isolated over here with the x. Moving that 3 to the right-hand side. If we square both sides, we're going to have distributive property on the right, and we're going to get rid of the radical sign on the left. That gives us 5x minus 1 on the left, but here I've got to expand this binomial, which is going to give us x squared minus 6x plus 9. So we want to collect all the terms on one side. So x squared minus 11x plus 10 is equal to 0. And if this trinomial factors, we'll get factors of 10 that add up to negative 11. We would use negative 10 and negative 1. So x minus 10 is equal to 0 when x is 10. And x minus 1, the second factor, is equal to 0 when x is 1. So next we need to check that work. This is important, so we want to see if x is 10 is 5 times 10 minus 1 plus 3 equal to 10. So this is the square root of 49, that's 7 plus 3. It is equal to 10. This one is true. So x equals 10 is a valid solution. And then 5 times 1 is 5 minus 1, that's the square root of 4, is the square root of 4 plus 3 equal to 1. And in that case, I believe we have an extraneous solution, because that is not true. The square root of 5 minus 1 is 4, and 4 plus 3 is equal to 7. It's not equal to 1, so this one is false. And x cannot be equal to 1. This one is extraneous, but x is equal to 10. So that solution holds, and we are good to go with one valid solution. X equals to 10. And if you're paying attention, when should you check for extraneous solutions? Well, it appears that whenever we raise an equation to a power, you need to check for extraneous solutions in that case. Whenever you raise any equation to a power, you want to go back and substitute and make sure that you have a true statement. In example 6, we're going to solve an equation with 2 radicals. So that can be a little bit tricky. You have to just be careful. We got square root of 5x plus 4. So I'll want to isolate one radical, and we can do that by adding the square root of x to the right side. And next we want to square both sides since the index is 2. So we end up with 5x plus 4 on the left. And if you expand this out, if you think 4 plus radical x twice, 4 plus radical x, and multiply, you've got 16, and then we'll have 2 4 radical x's, so that would be 8 radical x. And then radical x times radical x is just going to give us 1x for the right-hand side. Now let's collect like terms. So we got 5x here and 1x here. If we bring them to one side, we got 4x. And then 4 minus 16, we got minus 12 on this side. And 8 square roots of x on the right. So if you factor out a 4 from both sides, you got 4 here, and then on the right-hand side, we can divide both sides by 4 and end up with x minus 3 on the left and 2 radical x on the right. So again, I want to square both sides, so squaring the left and squaring the right. We'll have, again, a binomial on the left, so x squared minus 6x plus 9. And on the right, we have 2 squared, which is 4. and radical x squared, which is just x. So collecting like terms again, I'm going to move my work up to the right-hand side. We have x squared minus 10x plus 9. And factors of 9 that add up to negative 10 would be negative 9 and negative 1. So when x minus 9 is 0, x is 9. And when x minus 1 is 0, x is 1. And again, when I raise an equation to a power, I want to check for extraneous solutions. So plugging in 9 to our equation, we have 5 times 9. 5 times 9 is 45, and 45 plus 4 is 49, so that gives us 7. We're going to subtract the square root of 9, and the square root of 9 is 3, so 7 minus 3 is definitely 4. This is a good answer. Now when we try 1, 5 times 1, that's 5, plus 4, that's 9, and the square root of 1, and we want to know, is that equal to 4? So 9 minus 1, square root of 9 minus square root of 1 is 2, and that's not equal to 4. So x cannot be 1. X can only be 9, and 1 is extraneous. So x equals 9 is our solution. Then to finish the lesson, we have a real challenging problem. Let's give this a try. On the left-hand side, we want to move one radical over to the other side. So we could add the square root of x plus 1 to the right side. Then our next step would be to square both sides so we could at least eliminate one of our radicals. And on the left, we got 3x plus 1. But on the right, we want to square this binomial. I'm going to write it out so you can see what I'm thinking as I work. So we've got 2 times 2. This is 4. And we have 2 square roots of x plus 1. Then we have another 2 times the square root of x plus 1. And then we have a square root of x plus 1 times itself. So that's just going to give us x plus 1. And the 3x plus 1 on the left just stays the same. So here we have 4 and 1. That's 5. So we've got 5 plus 4 times the square root of x plus 1, and then an x. So our next step is to start over, and we want to isolate this one term by itself. So let's subtract x from both sides. That's going to give us 2x. And subtract 5 from both sides. That's going to give us 4. And we've got a 4 times a radical x plus 1. So if you see a factor of 2 that's common throughout, we can go factor out a 2 from the left and then divide 2 on both sides, which would leave x minus 2 on the left and 2 square roots of x plus 1 on the right. So once more, we want to get rid of this radical. We want to square this side. But whatever you do to the right, you've got to do the same thing to the left. So in this case, we've got a binomial on the left, which will give us x squared minus 4x plus 4. And on the right, 2 squared is 4. And the square root of x plus 1 is just x plus 1. So be sure to use parentheses here because we've got this factor of 4 in the front. And simplifying a little bit further, you'll see 4x plus 4. So we want to collect all the terms to one side, which gives us x squared minus 8x, and then the 4 minus the 4 is 0. So you can factor the left as x times the quantity x minus 8. So we want to look at x equals 0, and we want to look at x minus 8 equals 0 to see which is valid and which is not. So let's go back and revisit the original problem. So if we substitute 0 into the original equation, we have 3 times 0 plus 1, so that's the square root of 1, and then 0 plus 1, that's the square root of 1, and we want to know, is that 2? So the square root of 1 is 1, and the square root of 1 is 1, and that's definitely not 2. So x equals 0 is extraneous. This is extraneous. Can't do that one. Extraneous. And then checking for 8, you've got 3 times 8, that's 24. 24 plus 1 is 25. Square root of 25 is 5. And then we have 8 plus 1, that's 9. The square root of 9 is 3. And 5 minus 3 is definitely 2. So this one is a true statement. And finishing off our lesson with this really challenging problem shows us x equals 8 is a valid solution. And that is the end of lesson 5.